So if you're looking at this nice, smoothly animated background thinking, how the hell do you do that, Matt? Don't worry, because I'm going to be taking you through it. And in this video, we're going to be writing code for a custom shader, which responds to the scroll position. It uses a noise function to create this soft organic gradient, and it has an image texture tiled beneath it, and those are then mixed together to create something that some might say is impossible using CSS. If you want to see how I did this animated header, this scrolling image sequence, check out my other video. And as often is the case, I have the code available with the link in description. So if you want to just dive straight into the details and the implementation, that will be publicly available. If you do get value from this video or the code resource, please give me a thumbs up and support the channel. I'd really love to do more videos on shaders. Cool, let's dive in. Alrighty, so I'm going to assume that you have a somewhat basic understanding of Three.js. We're not really using many of the Three.js features here, certainly not kind of the 3D space aspect of it, but we are using the canvas, which is imported from React 3 Fiber. We're setting it to an orthographic camera, which is imported from React 3 Dre. And what this does is essentially gives us a sort of 2D camera, which in which the sort of scene is measured in pixels. And that's good if we want to just create a UI or a single background plane like we're doing here. So I've set up the background canvas, and I've created a custom backdrop plane component in here, which is a TypeScript component. You'll need to make sure that you've installed all the packages that are relevant. So we've got React 3 Dre, React 3 Fiber, 3 raw loader, GLSFI loader, GLSFI and GLSL noise. Quite a few. And the Next.js config is also required here in order to import your fragment and vertex files into the Next.js component. So yeah, remember to add this to your Next.js config. The shader material is imported from React 3 Dre as well. And this receives uniforms, a vertex shader, and a fragment shader. We'll get onto those in a minute. The uniforms are uniform values, so they're the same for every pixel. They're basically the props of the shader, which are passed into it from the JavaScript. You need to extend your shader in order to make it accessible as a JSX element. And that extend is imported from React 3 Fiber. Then what we've got is using the use3 hook from React 3 Fiber, we can read the viewport size. And as I mentioned a moment ago, the viewport size will be in pixels rather than meters or the standard 3D unit, because we're using that orthographic camera. And then we can just set the plane to have a width and height of the viewport. So if I say divide this by 2, we'll see that it will take up half of the screen, or a quarter of the screen. It's positioned just in the middle, and the backdrop plane shader is inside it, and it will be attaching itself as the material. So it will be responsible for coloring this. There's also an additional TypeScript declaration down here, and this prevents it from throwing the error of not recognizing what backdrop plane shader is. So as a boilerplate, this component is really ready to go and be extended and worked upon. It's fully type safe because we've got the ref, which is a shader material with our partial uniforms, defined our uniforms up here, although we haven't actually added any just yet. We will do. One more thing, in order to import the frag and vertex files, you'll need some sort of TypeScript declaration that lets Next.js know that it's or what it is basically, and it is just a string at the end of the day. So there we have it. That's the basic setup. Let's get into the fragment shader. The fragment shader is written in the GLSL shading language, which is strongly typed, and it's got a similar syntax to C. There'll be, for JavaScript developers, a slight learning curve here. You need to be extremely accurate with your typing. A single kind of missed semicolon will throw an error. If you define the wrong type here, this will throw an error. And you also can't log from within this function. The fragment shader is running simultaneously for every single texture pixel on the plane. So if we imagine that this is our plane here, every single one of these pixels will, the function will be run for. And so if we have, in this case, 1512 by 982, we've got, is that 1.4 million? And that's every frame. So we might be running that at 120 frames per second on a MacBook Pro. Now what's that? 178 million operations a second. And that's the reason why this code runs on the GPU as opposed to the CPU. The Book of Shaders is a great resource for learning more about these. Definitely recommend checking it out. The benefit to running it on the GPU over the CPU is that we can use parallel processing because the GPU has tens of thousands of cores, whereas a CPU may only have a handful, and you're just going to have a huge bottleneck of operations, which will result in a diminished frame rate. So now you kind of understand the shader, the language that it's written in. The purpose of them, or the purpose of the fragment shader, is to color the pixel or the texture or the coordinate on that plane. It's not necessarily a pixel on the display, it's more of a texture pixel or a texel. So if we take a look at this running now, you can see here we've got something that's not running. It was a moment ago. Yeah, okay, cool. So now we can see the color is determined by the value that the main function assigns to GL frag color. So every fragment shader has to assign GL color a vector for. The vector for, if you've not heard of it, is one of the data types, and it's basically a way of storing four floats. And floats are decimal numbers as opposed to an integer, which is a solid number. We also have Boolean, vec2, vec3. So vec2 is useful for, say, dimensions or a pointer position, something where you've got, say, a width and a height, or an x and a y. Vector 3 is useful for an RGB color without the alpha, or an XYZ coordinate. And then a vector 4 is some sort of matrix value or a RGBA. And so the GL frag color is a vector for RGBA. So if we put red to 1, these to 0, we'll have a fully red color, like so. And if we put them all to 1, then we have white. What I'm going to do is set up the size so that it is the full viewport. It's worth installing in your editor relevant extensions for working with GLSL. So there's this one, GLSL, which is I've got installed, GLSL lint, GLSL canvas, which probably don't need for what we're doing. And there's also GLSL literal. If you're writing your shader code inside JavaScript, you can get this nice code highlighting. So we kind of touched on the uniforms, and the uniforms are received from the JavaScript, whereas the varyings are received from the vertex shader. The vertex shader performs transformations on the vertex data. This is just the default I'm not doing anything vertex shader. It's not changing the shape of the plane. As we can see, it still just looks like a 2D piece of paper. It is, however, passing the UV coordinate into our fragment shader. So we've got varying UV, and it's just been assigned here. So that this vertex shader is needed in order for the fragment shader, or the shader material, to operate correctly. The UV coordinate is the position of the current texel. So if we imagine that this is running for all 10,000 pixels in my viewport, this function is running in parallel for all of those, but each one of those will be positioned slightly differently on that plane. And so this one up here will be running, this one will be running, and the UV coordinate is a value between 0 and 1 that is its position inside the grid, essentially. So this is, if this is our plane, up here is 0, 0, 0 on the x, 0 on the y. If we move along to here, we get to the 1 on the x, 0 on the y. And if we come down here, you see we've got 0 on the x, 1 on the y, or finally 1, 1, the bottom right corner. So what do you think this one would be? Right in the middle here. So that would have a UV coordinate of 0.5, 0.5. And anywhere else would have another corresponding value. So here would be, say, 0.2 on the X, 0.8 on the Y. This is where it does get confusing working with shaders, because you're no longer positioning things in absolute pixel terms or kind of units. You're doing them using a value that corresponds to the surface in which they're on. When you get a wider plane, so this is, let's say this is our viewport, it doesn't have a square aspect ratio. So 0.5, 0.5 will still be in the middle. But when it comes to working with images, we're going to have to make an adjustment to our coordinate in order to read the image data correctly. But we'll cover that later. Really, all you need to get your head around is that the fragment shader is running for every texture pixel simultaneously, and each one of those has their own coordinate, and that coordinate is a value between 0 and 1, which we can then use to set the color of that pixel. So if we say plug in the vuv.y value as our color value, because we can do that because the color value is just a range of between 0 and 1, is not a range of 0 to 255 like we're used to with the CSS. So we do this. What do we expect to see? At the very top left, or the very top, the first row is going to be 0, and the bottom row is going to be 1, and then everywhere in between is going to be a value between that. So at the top we'd expect it to be white. Sorry, yeah, expect it to be white going down to black. So now we've used a UV coordinate to create a gradient, and we can use the X value and it will fade horizontally. We can also mix these, and then we end up with 0, 0 being up here, but then this the Y changing the green, manipulating the green channel, which is why we've got fully green up here and not green down here. So now we've created a gradient using the UV coordinate. The GLSL language has some built-in functions for manipulating values. These are the building blocks for shaders. If we take a quick look at Shader Toy, this is a collection of shaders that have been written by far more skilled digital artists than I am. And just look at this, it's truly epic. It's one fragment shader with a ton of code I won't pretend to understand, but essentially built up from a series of smaller functions, loops within loops, and ultimately still outputting a fragment color for every coordinate in there, every pixel in there. The mix function is one of the more basic, but also one of the very useful function. And what we can do is we can create a couple of colors here. And then we can mix them using the mix function. So the mix function will take as its arguments 2 values, 3 values, where the third value is the value in which you're mixing it at. So if we check out Book of Shaders mix, you can see here that it's very useful for creating gradients. You can mix vector values or even float values. So it doesn't have to just be used for colors. It could be used for something else. But in this case, we've created an RGB color A, RGB color B, and we're then mixing them. And if we mix them using value 0.5, what I'm going to do is I'm going to reassign the color here. And now what we see is a mix between the red and the blue, a 50% mix because we've got 0.5. If we put, say, a 0.1, we're going to have 10% red, 90% blue. Sorry, the other way around. It's leaning heavily towards color A. So we're mixing mostly red, a little bit of B, sorry, a little bit of blue. 0 will just give us color A. Now if we put in the UVX coordinate, what we expect to see is a smooth interpolation between the red to the blue along the horizontal axis. So that's pretty cool. We can change it to Y. We can even do -X. And then we've got a diagonal gradient like that. Okay, so next up, we're going to look at the step and smooth step functions. I'm going to create 2 more colors. The step, if we can create a step value, the step function takes 2 arguments. The first is the value on which the second will be measured against. So in this case, it will return a 0 or a 1. So in this case, we're saying if x is less than 0.5, we return 0, and if it's greater than 0.5, we return 1. Now, with this value, we can create our output color, which will be a mix between color A and color B with the step value. So if the x is less than 0.5, it will be color, it will use color A, and if it's greater than, it will use color B. Can you guess what the result will be? So we've got a perfectly split set of 2 colors there. Now if we adjust the step, now what we're going to see is that there's only 20% green. Or in this case, now there's 90% green. This brings us on to the smooth step. So if I comment out that, the smooth step works similarly, except we have a range of values. And so if we set this to say 0.4 and 0.6, what we're saying now is if x is less than 0.4, we'll return 0. If it's greater than 0.6, we'll get back 1. And then anywhere in between will be smoothed or interpolated. So hence the name smoothstep. So what we can expect to see here is a gradient, but one that's happening within a smaller range. So yeah, we're fading it really across 20% of the entire X space. So if we change this to Y, we've got the same thing heading in that direction. We can play around with these values. And that's the smooth step. The smooth step is really useful for creating gradients or fading the edges of your texture. So you might want to use a smooth step for creating a kind of fog-like effect in the distance, or for creating soft shapes like a soft circle, which we may get onto in this video, or another one. I'm going to comment out the step related code, and we're going to look briefly at the sine and cosine functions. The sine and cosine values or functions can be used to return a value between -1 and 1, regardless of what the input is. So although generally the UVX coordinate is in the range of 0 to 1, if we multiply it by, say, 16 and pass it into the sine function, we're still going to get a value that is between -1 and 1. And this can be very useful. We can get a sine wave like this, and then we can use this to draw our gradient or work with time, because time is a value that will pass in and it will be ever increasing. So time could end up being in the thousands of seconds, but we can't really work with a value so large. So typically time would be passed into a sine or cosine function. Now if we take that out, let's get our colors back again. You actually notice here that I've defined these colors as RGB values, vector 3s, but it has to be outputted as a vector 4, which is including the transparency or the alpha. If I do this, we'll see the error in the console that a 3 component vector cannot be converted to a 4 component vector. So if you see anything like this in your error logs, it's usually that there's a value mismatch, a value type mismatch. And the solution here is to say, well, I want you to be a vector 4. So the first 3 values are spread in. So now we've got this funky wave. We can then say reduce the intensity of that. Now it's much more subtle, but you can still see it's here. It's kind of coming up over the bottles. You can increase these values here and get a more extreme effect or a more subtle one. And like this is already pretty cool. Like trying to create a gradient like this using CSS would be challenging. Obviously you could export an image, but then sometimes images look pixelated, especially when they're full size like that. All right, so this is where we're going to really start to benefit from working with fragment shaders. What we want to do is import a noise function. Noise is useful because it generates a kind of a random number that almost feels natural. The Perlin noise algorithm originated from the movie Tron back in the 80s. We'll see from this visualization that the input value increases along the x, but then this output doesn't jump up and down unexpectedly. It kind of follows a sort of pattern, and that's why it's suitable for textures or even manipulating shapes or models to give them a sort of a nice randomness. So in order to import noise, you've got a few options. You can just go and find some GLSL noise code online and literally copy and paste it into your shader. I prefer to use the GLSify function, and we've got that installed here, and we've got the loader installed, and in the Next.js config we're also using those. And what that allows us to do is import the npm package. We're requiring this GLSL function directly into ours. So when it runs, when it builds, it will analyze the shader files. It will look for this, and it will replace this with the source code. Essentially, it's just injecting it at the build time. And as I say, noise can give us a nice organic effect, and let's see what we can do. So we'll create noise value, call our noise function. Because we're using the 3D variation here, it's expecting a vector 3. So let's pass in the x, the y, and a random float. Then what we can do is we'll grab our colors, and we'll mix these using just the noise value to begin with, and we'll output that color. Okay, so now we've got a more organic kind of blob-like shape here already. If we multiply the x or the y, we start to see more kind of iterations of it appearing. So we do y times, say, 6. What about y times 60? Super streaky. So you can see here how if you increase that value enough, you end up with something that looks more like the noise we typically think of when we hear the word noise, like television noise. bad signal noise. But for what we're trying to create here, I want something that is more subtle than that. So I'll say leave it at 3 and 3. Actually, that's even too extreme. So that looks quite nice. Yeah, and so working with a shader, working with noise, you can create effects that are almost impossible with CSS. I know someone would say, no, you can do it, and I believe there are ways, but yeah. All right, I think now is a good time to pass in a uniform. So we have the use frame hook imported from React 3 Fiber, and this will run every frame in which the canvas is updating. So if we log this, we'll get thousands of logs. It has a state variable that we can read things from, such as the viewport, the pointer, the camera, the controls, the GL instance. What we want to do is pass time into our shader, because the shader code itself is stateless and stupid, really. It has no history, it has no record of what's happened before. So we need to give it a value of time in order for it to be able to animate. And we can do get elapsed time, or I think we can just do elapsed time like this. We'll need to add it to our JSX element. If all's gone well, we won't see an error. Now in the fragment shader, we have our float uTime uniform defined. If I put in the wrong value here, that will throw an error. If I forget to declare it, we won't be able to use it. It's important to prefix your uniforms with the character U, because then throughout your function code, you'll know that you're dealing with a uniform. Now what we can do is, if we replace the static value that we have in our noise function with the time, now this time value is going to be changing, which will cause our noise to change. So that's pretty cool. We can manipulate the effect the time has by slowing it down. And for something like a background, it's a secondary focus, so you don't want it to be going crazy. Seizure warning. You can write floats without the second value if you just put a decimal place or a dot. Okay, cool. So time is now manipulating our noise function, but I'm not happy with the colors. So let's head back to our shader and we'll define some new uniforms as our light color, which will be a color from 3, and our dark color. We can then set these as the default values here. And this is a 3JS color class, which has been initialized with a hex code. For this, I'm going to take two of my colors. Should we go light to dark, or maybe light? It's easy to change these later. Okay, we don't need to update the colors in the frame. If you wanted to pass in a dynamic color, say something that is the response of a user interaction, say if a user's hovering a button, perhaps you want to change a color, then you could pass it, you could set it in here, or you could set state, which would cause these uniforms to update. We need to define our two incoming color uniforms as u light color and u dark color. And what we can do is we can replace these colors with our light and dark color and check the result. Yeah, so now it's a lot more on brand. The next step is to pass an image into the shader. I found a texture from this website. These are kind of suitable for tiling, which is nice, but you could just have an image that you want to scale to fill the plane that you're shading. I mean, that looks pretty cool, doesn't it? So I've downloaded the texture image, and it's this. Well, actually, let's just open it up and see. It's this kind of black smudging one, which is like the effect. It's also got a kind of randomness to it. I think it will work well with the noise. So what I need to do is load the texture. And I can do this using the helper function from, again, Dre. So use texture. And use texture is like using a loader, a 3JS loader, and for texture with a texture loader. It's just a convenient hook. Now we want to import the texture image from our local file. Now it's not going to like this because Next.js image imports are static image data, but they do have a source on them. They also have a width and a height if you weren't aware of that, which can be handy. And then what we'll do is create the uniform for our texture. It's initially null because it won't have loaded. We'll assign it here. In our fragment shader, the type for an image texture is sampler 2D. This is 2D image data. And uTexture is its name. So now we can read the texture value. So we do vec4 texture color equals texture 2D. So texture 2D is another GLSL method in which you can give it your texture data and your current coordinate, and it will then return the color from that texture at that given coordinate. And then we can output that. So what I'm going to do is output the texture color. And it is actually there, it's just incredibly dark, so you won't be able to see it. And this is due to the way in which the shader handles its coloring. So what we'll need to do is actually convert the image color. And I found this online, but basically we can pass in a vector4 and get a new color value out of it. All right, cool. So now we can see our texture and it looks as we'd expect color-wise. We'll notice, however, that we have the problem with the scaling. So unless this is a square or the same aspect ratio as the image source, because the coordinate doesn't map up to the correct aspect ratio anymore, it's stretching it. And it's doing this in both directions. So in order to resolve this, we actually need to pass in the aspect ratio of our surface, our plane. So our plane has an underlying aspect ratio, which is, because it's set to the height or the dimensions of the viewport, the aspect ratio will be the viewport's aspect ratio. So what we'll do is we'll add another uniform for the aspect ratio, default it, and then in here we can just set it to the viewport's aspect ratio. Remember to add our new uniform at the top. Sometimes, you know, this Copilot just understands me. It's probably been reading my code for the last year. All right, now we've got the aspect ratio. A common pattern will be to define a local UV value that's initially assigned the original one, and then we can adjust it for the aspect ratio. Now I'm going to delete this stuff and delete that. So we've got our texture UV, and we'll use that value to read from our image. Okay, so we can immediately see that it's no longer distorting the image, which is good. However, we're not getting any image data over here. We're multiplying the x by itself times the aspect ratio. So if the aspect ratio is greater than 1, let's just log that. Aspect ratio is 0.89. So our x value is times by 0.9. it doesn't then know how to color the remaining thing. It's using like the last pixel from the image. We can use the fract function to tile it. So if we do texture UV equals fract texture UV, what we're doing now with the fract is always getting the fractional value, so it will always range between 0 and 1. So rather than us getting to 1 and then having a straight line of values like it was doing there without the fractional, it's just ending at this point. It will then go back down to 0 and color the next pixel based off of the start of the image. So move along. Okay, we're at the end. Back to the start. As you can see here, the fract function can be used for tiling. And with that, we've got a nice tiled image. There are ways in which you can scale the texture coordinate, texture UV, in order to fill the space rather than tile it like this. So you might want the texture to be stretched across the entire plane and cropped at the top and bottom, or vice versa, cropped on the left and right and stretching across the top. And you need to write a little like helper function to do that, which I won't cover here because that's not what we're trying to achieve. We can actually manipulate the texture coordinate using the time input. So if we say texture uv.y plus equals u time, now you see the value in which we're reading for the current UV coordinate is moving down, and then it's still it's kind of reset with the fract function. We can do that on the X as well. And then we get a horizontal scrolling background. Slow it down. So this is quite neat because we've just got one image that's been tiled seamlessly and is moving really smoothly. So next up, we want to mix our noise color with our texture color. So let's rename this noise color. Create a vector 4 for our final color. And yeah, it must be listening. So we're going to mix our our noise color vector 3 as a vector 4 with full opacity with our texture color at, oh, actually it's not listening, it's just copied something I'd written down already. And if we do 0.5, we'll get an even mix between the two of them. Oh, we need to remember to return that color, but we also need to convert that first. So we've converted the texture to sRGB, then we're mixing it, and then we're going to output the final color. All right, so that is looking really cool, I think. I don't want the texture to be so extreme, maybe sort of something like that. 25% texture, 75% noise gradient. Cool. That is looking great. What if we want to move the texture or the image, the background image, based off of the scroll position? So we can do that through, you guessed it, another uniform, which will be a float, and it will be the scroll offset. And then inside our component, we can create a new use GSAP hook, which is similar to a use effect. No dependencies, new scroll trigger, so import that, create it, start at 0, end at max scroll, and on update we can get the progress, which will be in the range of 0 to 1. And then what we want to do is we want to pass this progress value into our shaders uniform. Scroll offset is going to start at 0. And I'll create a ref to hold that value. And then we'll set it here. And then down here we can assign the uniform our local ref value. Nothing's changed because we aren't handling it in here. Now we've got the scroll offset, we can either move the image texture, or we can say change the noise, or we could even actually just manipulate the UV coordinates for both, which would then cause the texture and the gradient to move at the same time. So I think that's what I'll do here actually. I'm going to create a vec2 UV equals VUV. Then I'll do UV.y plus equals scroll offset. Rather than passing in the varying, I'll pass in the value which has the scroll offset set to its y, or impacting its y. We'll do that. So now we'll see that both the image and the gradient are moving together. So if we check out, say, when a dark section appears here, that's moving with the background texture. Now, I think that the X movement is still a bit extreme. I want it to be really subtle. And in fact, I could actually just put this manipulation on to the UV coordinate here. And then we get we might want to move it in the opposite direction so we can minus it. Now it's like it's scrolling up as part of the page content. Just play with this on my trackpad so I can get a smoother scroll. Yeah, it's looking good. I don't know if the background though is a bit too bright, so I think I'm gonna swap that light color for this one. So we can change our uniform here. And actually, are the colors colors aren't displaying properly, which is an issue that I didn't tackle earlier because I didn't realize it. But I think what we want is to put this conversion on these colors. Yeah, so now they actually appear as they do in the Figma file, whereas previously it wasn't matching up without that. So yeah, when you're passing a color into a shader, you need to convert it in the same way that we were converting the image color in our little function here. All right, I actually want to use the darker color. So to finish this off, we'll change that. It's looking pretty cool. I think the texture's a bit too strong. All right. So there we have it. Running extremely smoothly, responding to the scroll position, using time to animate it when there's no other input, using noise to generate gradient shapes that would be otherwise impossible. Don't like to use that word, but very challenging. Passing in a texture image which is tiled, retaining its aspect ratio, all within a type-safe React 3 fiber component. And I believe that's that. If you've made it this far, please consider giving this video a thumbs up and subscribing if you haven't already. I'd love to do more videos on shaders. I am still learning about all the incredible possibilities myself. The code is available in the public pragmatic tutorials repo, which is found in the description. And yeah, look forward to seeing you again. Peace. Bye.